So hello, everybody. I too will give a Maori greeting. I can't say it right, but I am from Los Alamos National Lab, and we have mountains on both sides of the Rio Grande Rift. I live on one side, the lab is on the other. And my name is Laura Monroe. I gave this talk, I gave another talk a few years ago, just before COVID here, and I found this saying, and I thought it was pretty appropriate. It takes a while to make those nice greenstone things, but they carry a lot of meaning, they point in a lot of directions, and that seems like us. So last time I was here, thank you again for inviting me, I really appreciate it. Last time I was here, I spoke about inexact and probabilistic computing. And that's all about randomness, and it was targeting emerging technology. Quoting Terry Tao, who is a Fields medalist, he studies these things. Those kinds of things are addressed via analysis and probability, continuous mathematics. This time I'm going to talk about a mathematical approach to network design. And this is extremely structured. It's just like the polar opposite of what I talked about before. And it's aimed at emerging technology, in particular optical technology and next-gen networking needs. And you address that through discrete mathematics in general, number theory, that kinds of things, which is my training. So that's more like what I do. And the last time I was here, I went by the City Art Gallery, and I saw that particular art piece, and I just liked it so much because it certainly spoke to what I was speaking about then. You have this nice mathematical concept of a computer, and then you have reality impinging on it on more or less inconvenient ways. So last time I was talking about all the mess. This time I'm talking about the actual grid. So my talk's going to be on post-exascale network topologies, and it's going to be kind of different from everything we've discussed earlier. It's much more first principles, it's much more mathematical, and that's what the focus is here. I want to call out the team of people I'm working with. I'm working with Fabrizio from Intel, Kartik. I'm working with a former student of mine who's now a professor, a math professor at Colgate, and I'm working with Torsten and Maciej Besta from Zurich. And it's really great to work with this kind of a crowd of people because it's so interdisciplinary. I mean, I've heard people talk about, mention interdisciplinary work at this meeting, and that's really all I do. This is especially interdisciplinary. It happens that mathematicians and computer scientists think differently and they approach things differently. All computer scientists are mathematically literate, but they just have a different approach. And it's really fun speaking across the disciplines. Sometimes you actually even have to establish a dictionary for it to actually communicate nicely. So on this team, we have networking people, we have hardcore computer science people, we have hardcore theoretical mathematicians, and it's been really fun. So what I'm going to discuss today, I'm going to just briefly touch on the problem and the motivation. Karen spoke about optical a couple of days ago, did a much better job than I could possibly do. And that's just sort of to touch base on what we're doing. But I'm going to discuss a little bit about the constraints we have and the opportunities that are now afforded. And I'm going to spend a fair amount of time talking about the basic design. Now, what I want to do here is I don't want to go through a bunch of proofs and everything. It's my experience. You have to sit down and study those things anyway. You never can just hear them. It just never happens. I want to give people a feeling for what we're doing. And for the first time, I'm going to present a new best-sized mathematical graph. This is kind of a big deal. It's bigger than any we're known for that parameter. And it's in submission now, but I'm going to discuss it here for the first time it's been discussed publicly. And there will be a little discussion about future discussion, or future directions. So the basic point here is networks are graphs. Graph theory is a very mature field of mathematics. They've been studying it forever. And what we want to do is harness some of the machinery that's provided because these days the new technology affords new opportunities. Old networks do not properly exploit it. And that's the subject of my talk. So first, the problem statement. What we're looking for is to find an optical network of given diameter for routers of a given radix. And the router is the router, and you can predict how, what it's going to do in the nearish future. Certainly, Intel can advise us very well on that. But the problem is just basically mathematical. So first, a little motivation. We've got these new technologies, photonics, high connectivity scaling, where you've got really high-radix routers. That means the graphs have each node has large degree. And so we're taking a formal mathematical approach to this. In our preliminary results, we've got an asymptotic best case for diameter 2, and we have now the best known results for diameter 3. They're the best known. And the challenge is we're still far from the best bound for diameter 3. So hopefully there's a lot of room to progress. So the technology, we're aiming at photonics co-packaging, but this could work for a large-scale data system as well. And here are some numbers. They come from Fabrizio. I think this one about how many fit on a thumbnail is not quite right. From what I learned the other day, they're even smaller now. And there's challenges, as Karen pointed out. The network challenges, we want to connect around 100K nodes or network endpoints. And we want to deliver scalable all-to-all performance, cost-effective, manufacturable, fault-tolerant, of course, and you achieve that through technology and system innovation. But the network is going to be different. It's not going to be enough to hook it up to a fat tree or Dragonfly. So how do we wire that kind of a network? Well, we're going to start with a mathematical bound called the Moore bound. And the state of the art right now is about 15% efficiency in terms of the number of actual nodes you get for the network of the given radix and diameter. And we've got a new result for diameter 2, which is optimality, but it's only a few thousand nodes. So constraints, opportunities, desires. What do we have to do? What do we want to do? So the more routers a packet goes through, the more latency you have, congestion, delay. As I understand it, when you're doing optical, it's speed of light. So between routers, it's fast. It really is not bad. But when you hit a router, things slow down. They have to be taken intake, processed, and sent out again. And that's where the latency comes from. So what we're trying to do is minimize the number of actual routers you hit, minimize the number of hops. And the total network latency that we're working with is this equation at the bottom. So what are we after? Well, first of all, we've got an opportunity. We've got these high-radix routers. They're much bigger radix than before. That means we can fit a lot more edges on and get the diameter, the number of hops down. The constraint is, as I said before, we want not very many hops, a very low diameter. What do we want? Lots of nodes. We want to support as big of a system as possible. And we also want there to be exploitable structure. I mean, there are randomized networks, and that's great. You can get bounds using those. But you can't do all that much with exploiting the structure. Perhaps you know where triangles are. Perhaps you know how it gets laid out. And we would like to have that, and mathematics does provide that. So here's your naive approach. Basically, you take a bunch of nodes, they've got a given degree, and this is sort of a representation. You can see each of those nodes. That's got degree, the leftmost one has degree 4. Some of the nodes have degree 3, and it goes downward. All right. Naively, and you set a desired diameter, and in this case, we're going to talk about diameter 2 hops, and connect the nodes. But you want to retain the degree and diameter. So you can, sort of look at it like, how do you fit the biggest number of edges and put actual, you can add nodes as you like, but don't increase the degree and don't increase the diameter. And that's naive. But it's basically what we're doing. So mathematically, we actually have an upper bound on network size. It's called the Moore bound. So again, we want as high of a degree as the near-term routers will support. We want not too many hops, so low diameter. We want usable structure if we can get it, and lots of nodes. And this happens to be a classical problem from mathematics called the degree diameter problem. What is the order, the number of nodes, of the largest graph with a given degree and diameter? And this is good that there's a classical problem, because it means smart people have been working on it for a while. Maybe it's a little bit less good because it's still an open problem. It depends on how you look at it. It means we can make good progress on it, perhaps, but it also means people haven't done it before. So it's not just out there to pick off the tree. So we have a bound. It's called the Moore bound. So if D is the graph degree, or the router radix, and K is the diameter, or the maximum amount of hops you're going to permit, this is your bound, and it's a mathematical upper bound. You cannot get more nodes than this. You're stuck with it. And what we want to do is maximize this as best as possible. So the first question is, can you always find a graph that hits this? And the answer is no. First of all, let's look at what the actual bounds are. Okay, one hop, that's just a complete graph, and in one hop you can reach everything. You can reach D different destinations. In 2 hops, you can reach D squared plus 2 destinations, where D is the degree. And here's some numbers. For D equals 64, the bound is 4,097. So it's not that huge. In 3 hops, you can reach order D cubed, different destinations. And now you're talking. Now that starts to be really a rather large graph at that point. And these sizes of routers are within reach. They're either here now or they will be here shortly. Do any graphs actually meet it? Yes, but not too many. The complete graphs do. We're never going to, well, we might for certain cases, but in general, we're not going to make a complete graph network. The cycles, yeah, they do, but who cares? That's a circle, basically. And we're not going to do that either. Then there are a couple of special cases, which I've got a picture of them here. There's the Peterson graph, and that's one graph. You see it right here. It's not a family. And the Hoffman-Singleton graph, that's also one graph, degree 7. And there's just not a lot of design points. So if you happen to want to do those exact things, you're in business, but otherwise, no. And then there's a degree 57, which we don't even know if it exists. There's a lot of papers about things that would surround it. And that's it. That's all that meets the Moore bound. But asymptotically, we actually do. We have graphs that are very, very good, and they come arbitrarily close to the Moore bound. And I'm going to spend a lot of my talk talking about this. They're old. Erdős, Rendy, and Rennie put together a paper in 1962. That's probably before most of us were born. Brown also independently did it. It turns out a mathematician named Singer did the same thing in 1936, but he went about it through a totally different path. And it wasn't until the 2010s that they were noticed or shown to be isomorphic. And they're from projective geometry over a finite field. And we have a projective geometer, a geometer on the staff. That's my colleague, Kelly Isham. So I'm going to I want to give people in this section a feeling for how they're actually constructed. And they're a geometrical kind of thing. They're constructed with geometry. You use a little bit of Galois theory. So let's start out with we're just talking about geometry here. And let's say you have 2 vectors, L0, L1. And you know from basic geometry, there's a vector that's perpendicular to both. Like if you look over there, okay, there is your 2 vectors, and you have M coming out like that. And that's Euclidean geometry. We all know that. And it's the cross product. So what if we constructed a graph with edges that express dot product perpendicularity? And so graphs always when you have a graph with edges always express a relationship. And here the relationship is perpendicularity. So if you call L0, M, and L1 nodes in the graph, then L0 is perpendicular to M. You've got an edge between them, and M is perpendicular to L1. And because you always have, for any 2 edges, you always have an edge that is perpendicular to both, you've got a graph of diameter 2 then, because you can always go through that. So now we're going to move into Galois theory. That's fine when you're in Euclidean space. Unfortunately, that gives you an infinite number of vectors, and we're not going to do an infinitely large computer. What we're going to use is a finite field. And you use FQ of their vectors of dimension 3, and you use those vectors whose first non-zero entry is 1. And there's some facts about it. The degree is going to be q plus 1 in that case, and you've got a more bound, q squared plus 2q plus 2. And it's a fact that the number of vectors is q squared plus q plus 1. So that's really very good. It's really very close to the more bound. So how do you construct these graphs? It's actually very easy to do. You use dot product perpendicularity, and it's exactly the same as Euclidean dot product. And in this talk, we're just going to talk, the finite field is just going to be a prime q. It's going to be arithmetic mod q. It makes life easier. The principle is the same if you have a finite field that's a prime power. It's just the arithmetic's a little different. You have to work out the table ahead of time. But it's the same principle. And the incidence relationship, once again, is perpendicularity. It's defined by the dot product. And one comment, the length doesn't matter. It doesn't matter if you've got, like, if that vector goes all the way from the floor to the ceiling, or if it's an inch long, you still have the same perpendicular relationship. So you can just divide through by the value of the first non-zero element, and you get a kind of a standard representation. So I'm going to do a little quick example. Let's say we've got our prime is 3, and just arrange the vectors mod 3 in some layout. And I just did lexicographic here because it was easy. So you've got an edge of the dot product is 0 mod 3. And for example, 110.120, that's going to be 1 plus 2 plus 0, and that's 0 mod 3. So you got an edge there. And these are all the edges. This is the graph right here. And it happens that some vectors are self-perpendicular. That's special. We don't have that in Euclidean space. No vector is perpendicular to itself. But you can see like 111.111, you get 0 mod 3. And those vectors have degree 3 and not 4. We're not counting their little self-loop. And there's a lot of useful structure here, which is great. And I'll discuss that a little bit more. So here's a few facts about ERQ. It has diameter 2 because it's based on perpendicularity. You've got q squared plus q plus 1 nodes. Each non-quadric node, so non-self-orthogonal node, has degree q plus 1. And you've got this more bound, as I discussed earlier. And it asymptotically approaches the more bound. So this looks very promising. What if we made a network out of it? How would it compare? So we introduced PolarFly at supercomputing this past year, and we presented it there. Here is a more bound comparison of diameter 2 topologies. And so we've got PolarFly, we've got SlimFly, which my colleague Maciej Besta presented several years ago. The Peterson graph, and that's one of those little dots up near in the left-hand corner there that does meet the more bound, but there's only one of them. HyperX is that low curve right there. You can, even though it's used a lot, you can see it's not doing too well as far as the more bound goes. And if you want to read this paper, it's out on the archive. You can just search on PolarFly. One nice thing about this is it's got good coverage of possible radixes. It doesn't cover everything. Your degree is q plus 1, and your q has to be a prime power. So clearly, you're not going to hit everything. But think about the prime powers it does hit. It hits 23, so 24 is the degree, and that matches nicely with the router. It hits 31, that's a prime. So 32, we have routers like that. It hits 47, prime. 48, you might have a router like that. It doesn't hit 63, unfortunately. It does hit 61. So there might be a little bit of waste in there. It's also quite scalable. HyperX, for example, you need radix 62 to connect 1,000 nodes, and that's a lot of cables as well. PolarFly gets the same scale with radix 33. So that's a smaller router. And many fewer cables, half as many. So that translates to cost saving. By section width, we had to look at this. We used Metis to analyze it. And it's asymptotically optimal. It's approaching the best. It does a lot. Again, it does better than Dragonfly. Slimfly isn't too bad, but it still isn't quite up to what Polarfly does. Fat Tree does well. How about path diversity? There's a lot of it. It happens that you only have, for any two nodes, you only have one path of length 2. So there's not path diversity there. But you have a lot of paths of length 3 if one of them is not quadric and they're not adjacent. And you've got even more of length 4. It's going up, you've got Q at length 3, Q squared of length 4, et cetera. So you have path diversity as well. So a good diameter 2 graph, it's got potential. It shows good scalability, and it's easy to construct just via the dot products. So how do we lay it out? So I'm going to now show a few Polarfly layouts. We have basically 4 types of vertices. The quadrics, so those are the ones that are self-orthogonal, and there's Q plus 1 of those, where Q is your Q plus 1 is your degree. Centers, they're a special thing that one of the quadrics is attached to. And then you've got the V1 and V2 vertices that each center is attached to. So you start with all the self-perpendicular quadrics, and they form a cluster. And in this graph picture, I put those up on top. Pick one of them as the starter quadric, and take all the vectors that are perpendicular to that starter quadric, and those are the centers. Call them the centers. Each center starts its own cluster, and all the vectors are in that cluster are perpendicular to that center. So what you end up with is you end up with Q plus 1 clusters, and you could put them in different racks or however you want to, whatever you choose to lay them out. And it's going to consist of the quadrics and then each of these little clusters that look like this. There's also good connectivity between clusters. So here I've shown in black 2 clusters, and you can see blue and green, the connectivity between them. And each non-quadric cluster has Q minus 2 connections to any other non-quadric cluster. And it also has Q plus 1 connections to the quadric cluster. So you have well-defined connections between them. So structural aspects. I said there was structure. There is structure. Here's a bunch of Polarflies for primes Q equals 11, 13, 17, and 19. And remember, the degree is Q plus 1. One of the things interesting with this is you can see that each cluster has a nice fan out. You have the center, and then you have a bunch of triangles coming out from it. Triangles between non-quadric clusters. Now this is, it's a fact that if you take any of these non-quadric clusters, that there's exactly, you take a triplet of them, there's exactly one triangle that joins them. And it took us a month to prove that. We'd like to be able to exploit it in some way. We haven't thought of how, but it's an interesting mathematical fact. And what I'm showing here is just taking that top left cluster, and I've drawn the actual triangles connecting it to pairs of other clusters. This is interesting. There's different ways to lay it out, and it shows off different kinds of qualities. For example, the left-hand one is just arranging them in lexicographic order, and it looks like a mess, doesn't it? It just looks like, there's a lot of edges there, and great, awesome, but what do you do with it? Look at the second from the right. That's the cluster view that I mentioned. You can see the triangles there. You can see the structure, and all the edges are rendered there. They're in light gray. Look at the far right. Now, that's really interesting. It's colored. These are all the exact same graph. It's Q equals 7, degree equals 8, and that right-hand one is just a different rearrangement of all the nodes. And you can see the parallelism there. It's amazing. And we're working to exploit that. There's a mathematical reason for that. We're working to exploit it right now for other purposes. And that's what I mean about structure. If you have mathematical structure, you may be able to exploit it. So I know you believe me that everything is, this is a 2-hop graph, but I'm going to show it to you anyway. It's always nice to see it. So let's start with the starter quadric. Okay, here's everything that's 1 hop away, everything that's 2 hop away, and we're there. Same with another quadric, 1 hop away, 2 hops away. And you've hit all the nodes there. Let's start with a center. 1 hop away, 2 hops away. V1 element, that's one of the things that's joined. 1 hop, 2 hops. A V2, 1 hop, 2 hops. And so this, it would be great if this was so structured as to be perfectly symmetrical. It's not. The quadrics are different than all the other elements. The centers and the V1s are different from all the other elements, and the V2s are different. But all the centers, for example, are the same. They behave the same. All the quadrics behave the same. So there's a fair amount of regularity. Now, the problem is diameter 2 isn't quite good enough. We're looking at post-exascale. 4,000 nodes won't do it. So in 2 hops, remember, we can reach d squared plus 1 destinations, and the degree is in the thousands. In 3 hops, you can reach, for degree equals, for the router radix equals 64, the bound is 258,000, and that's a lot of nodes. It happens that Polarfly, which is diameter 2, it's optimal for diameter 2 networks, but you just don't get that many nodes. So we're looking at diameter 3 now. All right, so this is an interesting graph. This is actually taken from data from the Combinatorics wiki. And you can see the little triangles there. Those are diameter 2. And as a percentage of the Moore bound, it's close. Diameter 3, it's nowhere close. Look, you get up to degree 19 or 20, which isn't that big, and you're in the 25% range. That's not very good. And so we're looking to find graphs that are a lot closer to 100% there. All right, so now there's something important I have to say about that bound. That is a bound, and it's not even necessarily tight. We don't know. There may or may not be graphs, diameter 3 graphs, that are close to 100% of the Moore bounds. We know there are none that actually meet it. That's known. But there might be diameter 3 graphs of 95%, or it might be that 30% is the best you can do. We don't know. Mathematicians don't know. So that's what we're looking at right now. Can we improve that? So let's have a look at diameter 3 networks. Here's your Dragonfly topology, and its Moore bound comparison is on the 15% range. It's not great. Number of nodes. Here's Bundlefly, and this was just introduced a couple of years ago, and it's 25 to 27% of the Moore bound, and that's pretty good. Here's our new graph, and it's called Polar Star. And it's a star product extension of Polarfly itself, and it's a new record size graph. It's bigger than any known for larger diameter. It's a star product extension of Polarfly. It's 30% of the Moore bound. It's 31% bigger than the state-of-the-art Bundlefly, and it's 2 times bigger than Dragonfly. So I'm going to quickly go through Polar Star. I think I showed the, yes. This paper is out on the archive. We just put it out like yesterday or a couple of days ago. If you want to look it up, look for Polar Star, and you can read it in more detail. So what it is, it's a graph product construction, and it's a little bit complicated. Basically, you start with a good graph, a good basic graph as a structure graph that has a lot of nodes. We're going to call that the structure graph, and we're going to use Polarfly. And then you have another graph that has a specific property. It has a bijection on it that if you apply that bijection to the edges and take the union of those with the original edges, you get all edges. You get the complete graph. And taking the product of these and joining the graphs together, you basically substitute a structure graph for every node, or a supernode for every node of the structure graph, and join the supernodes together, and you get a really good graph, provably so. And we've proved that in the paper. A diameter is diameter of the structure graph plus 1. The degree, you just add the 2 degrees, and the number of nodes, you multiply them. So start with polar fly as the structure graph, and this is a really simple polar fly. It's only degree 4, but it's easier to look at. Okay, here's a newly devised graph. This particular one is a Paley, but we have other newly devised graphs, inductive quads, we call them, as supernodes. And you can see, so the green is the original supernode, and then the 2 green that are joined together, that's how you actually join them, according to that function that I just discussed. And you replace the nodes with the supernode, then you get the star product. That is the star product. And you can see the structure there. It looks pretty much the same. So here's a degree 11 polar star looked at from above in that layout. And you can see the little supernode, you can see the nodes here, but you can see the supernode graphs here, and all the edges are represented in gray. So let's do a few comparisons here. Scalability, it's quite scalable. Dragonfly requires network radix 62 to connect 35K nodes, and Polar Star achieves the same scale with 50, radix 50. I want to point out what we're looking for is even more improvement. So we're at about 30%. Can we get 3.5 times improvement on that? And the inspiration is, note those 3 little triangles up there. That's something called a DeLorme graph, and it's just great. It really does approach, for diameter 3, it approaches more bound asymptotically. However, unfortunately, there's only a few radixes that it works for, and we want better coverage than that. So that's our inspiration. DeLorme, as I say, only a few constructions exist, but it's tempting. So the holy grail would be achieving the same polar fly DeLorme efficiency of scale, and that's the challenge. And when I say it's a challenge, it's actually non-trivial. We have funding, my colleague Kelly, the mathematician, and I, we have funding to study this. We're bringing on students. We may or may not get there, because it may or may not be mathematically possible. And so we're looking into it. We're looking into other things that can be done. You know, perhaps you don't have a perfect 3-hop. Maybe you have a 3-hop with a few of the paths are 4 hops. Okay, that's also, we would certainly consider that. We'd certainly be interested in that. So the takeaways for this talk are basically, you've got architectural needs, which you want to line up you want to join a whole lot of nodes together. You've got new technology, which both imposes, both gives you opportunities with higher radix, and also sort of, it's an impetus to do more. You know, if you've got like tiny latency between nodes, well, now the target is reduce the number of nodes so you have even less. And then good mathematical design gives you next-gen networking. So the basic point is emerging technologies gives you opportunities, but the networks have to be mathematically designed. It's not enough. It's not going to be enough just to take a naive approach and, you know, put something together that kind of works. If you really want to maximize it, you have to have mathematical approach. So we've shown optimal diameter 2 networks. We've constructed the best known diameter 3. We don't know if it's optimal. Maybe it is, maybe not. Record graphs, and we aren't near the diameter 3 bound. And nor have we looked at, this is an important point, nor have we looked at all the promising graph constructions. Graph theory is large, and this is a large research project. So this is a start, and the research is continuing into both the devising the graphs and deducting properties of the graphs.